Good morning, guys. Today I want to wrap up our unit on designing studies by talking about scope of inference. What is scope of inference? It's a big fancy way of saying what did we learn and who does it apply to. So that's what I want to focus on. What did we learn and who does it apply to? Or to whom does it apply? So there's two questions that we can answer that are going to tell us the scope, the breadth of the results of our study. So when we say what did we learn, we're wanting to know, did we just find that there's a link between two variables or three variables or however we're looking at? Or did we find that one actually caused the changes in the other one? So did we find a cause and effect relationship? And to whom does it apply? That means, are we talking about just the individuals who participate in our study, or is there some larger population we can kind of generalize those results to? That's what we mean by scope of inference. The two questions that will answer that are these two. Did we randomly select the participants for the study, and did we randomly assign individuals to treatment groups? So why do we care about randomly selecting participants for a study? Well, as we talked about before, randomization helps us control those other little influences, those things that help us or cause us to not accurately represent what's going on, right? What did we call that when we weren't accurately representing what was going on in a population? We called that bias. So randomization helps to minimize bias because it brings in all those little elements from the population, those little characteristics from the population, and scatters them through our samples. So the purpose for randomly selecting participants is to minimize bias. So if we randomly selected individuals, we've minimized bias, we've used some random technique. What we've done is created a group of people, a sample or group of individuals that look like the population. Well, what do we call it when we have a group that looks like our population? A representative sample. It represents the population. So if we're answering yes to this question, yes, we have a representative sample. Yes, we randomly selected participants for the study. What we conclude is that we can generalize our results to a greater population. Now on the other side, say we did not randomly select participants. Say we just walked up and talked to the first 100 people or 200 people that we saw, and they happened to all be located near each other, did a convenient sample. So we did not randomly select, we did not minimize bias. So what we have is a non-representative sample. And if it's a non-representative sample, then we didn't learn about the whole population because there may be some characteristics of that group that are explaining why they're answering the way that they are instead of characteristics of the population that they're actually trying to represent. So because they are non-representative, we're not learning about the whole population. We are limited to only learning about those individuals who participated in the study. Only those who participated in the study. That's all we've learned about. Think of it like we talked about when we did our voluntary response sample. If I ask people to, if I put a petition out there, or I put a flyer out there, or I send emails to people, and then they choose to respond, I'm not learning about the population as a whole, I'm learning about the people that cared enough to respond. So that's what I've learned about, people who are highly invested or highly interested in that topic. So that's what we mean by who does it apply to. Did we randomly select individuals? Yes, we got a representative sample, so we can generalize to our population. Or no, we got a non-representative sample, so we really only learned about those who were in the study. Now the next part, what did we learn? did we randomly assign individuals to treatment groups? Why do we need to randomly assign individuals to treatment groups? We talked before in our experimental design that randomization helps to minimize not bias, but confounding. It helps to take those other explanations, those other variables that could influence why an individual responds the way it does to a treatment. It could take those and then scatter it amongst our treatment groups. So that's why we're randomly assigning amongst the treatment groups. So this is meant to minimize confounding. Just trying to cut back on those other possible explanations, other possible influences. Well, what do we learn about? Well, when is it that we do randomization? Well, if we are randomly assigning things, that's an element of an experiment. So this is typically a feature of experiments. Now, if we've done a well-designed randomized experiment, what have we learned? Well, what we've learned is all those other influences, all those other variables that could be causing a change in our response and our measurement are probably not the case because we tried to get them into both treatment group and non-treatment group. So since those have been eliminated or minimized their chances of, never eliminated, but we've minimized their chances of influencing the response, what we've done is isolated that explanatory variable. So if we've isolated the explanatory variable, we've said that this is it. This is the reason, assuming we find that there's statistically significant differences. This is the reason for the change. So what happens for a randomization, we can actually infer a cause and effect relationship. And this is huge. This is what we really want all the time when we do studies. I want to know, does one thing cause another thing or influence another thing or make another thing to happen? But to have that, I need to have a well-designed randomized experiment. I need to have tried to get my hands on and control on as many of those other possible explanations. So that's what our goal is, not always possible though. Sometimes we get situations where it's not possible to randomly assign individuals to treatment groups. Sometimes they're just stuck with the explanatory variable. So if I was doing something off of eye color, I could put contacts in somebody, but if I'm talking about true eye color and how they react to their own eye color, I can't randomly assign somebody an eye color. So that's a situation where we're not able to randomly assign what's going on. That would be known as an observational study. So typically, this isn't always the case, but typically, if we have no random assignment, we're dealing with observational. All observational studies have no random assignment, but not all no random assignments have are observational studies. But typically, this is how it works, especially for this course. So if we did not randomly assign individuals to treatment groups, what we're doing is we're just observing what's occurring naturally. We didn't put our hands on any of those confounding variables. And because we didn't minimize confounding, those may be the cause for the change still. Those things going on in the background that we didn't measure, they may be the cause for the difference. So when we are looking at an observational study or no random assignment, what typically happens is we can find association but not necessarily causation. I know these two things are linked, but I don't know that the one caused the other to happen because it was observational. There were a lot of other things. So if I'm talking about eye color versus eyesight, whether or not you wear glasses, I can't assign people different eye colors and then test their eyesight, right? I have to just go with the people that have a certain eye color and measure their eyesight and go with other people that have another color and measure their eyesight. It's observational. I might see that people with darker eyes are more likely to wear glasses. There's an association there. That's just based on a study I had students do a few years ago. I don't know if that's actually accurate for the whole population. Might be able to find an association between that, but I don't know that the darker eyes are causing them to need to wear glasses or contacts or whatever it is. There may be other background variables, background traits that cause poor eyesight that are also causing that certain eye color. So eye color could be an indicator, but not necessarily a cause. I don't know because I didn't get my hands on those other variables. We didn't do a randomized controlled experiment. So in that vein of not being able to know or not being able to work a randomly assigned controlled experiment, how do we still get causation? Well, we can get causation still by meeting some very, very rigorous standards. So to get causation when a randomized experiment is not possible, so what are some situations where it might not be possible to do an experiment? But we may really need to know, is there a cause and effect relationship? Eye color in glasses, not a big deal if we know if it's association or if it's causation. But what if we're talking about smoking and lung cancer? That might be something where we want to see, does this activity, something we choose to do, could it potentially be harmful? So is there harm in it? That's a situation where we probably can't do a randomized experiment. Think about what you're asking somebody to do in that case. You're saying, we think this could possibly kill you, and we're going to randomly decide or randomly assign half of a group to go do something that's potentially deadly. And if we're right, it is deadly, it will be killing them, most likely. And then the other group, you're not going to. So it's very unethical to run an experiment in that situation. Doing a true experiment on texting and driving, same idea. If we were going to, not in a simulator, but test on the road, that's not something you would want to do as a randomized experiment. I don't want to assign some people to text and drive thinking that they're probably going to get in a wreck and maybe kill someone, and then others to not. So because a randomized experiment isn't always possible and reasonable and ethical, but sometimes it's still very, very necessary to try to get that cause and effect conclusion, we've set up other kind of things that we can look for. So first off, we want to see, is the association strong? So when I look at these, do I see a clear, very big difference in those two? So there's strong statistical significance there. So is the association strong? Is it consistent? So do we feel like it's small values lead to a certain type of value, and then small or larger explanatory values lead to other type values? So I'm not getting a graph that's kind of, if we're thinking quantitative data, that kind of waves in and out. I want something that kind of stays in a tight, clean, recognizable pattern. This association is consistent. Larger values of the explanatory variable are associated with stronger responses. So in that case, as we increase the size, we're talking about getting a much tighter individual, or tighter picture. And then the alleged cause precedes the effect in time. So that's another one where it's reasonable to say that you were texting before you got into your wreck, correct? Or you were smoking before you got lung cancer. Those are things that we reasonably could see happening one before the other. And then the alleged cause is plausible. It's reasonable that you are distracted, or you have something in front of your eyes and taking your eyes off of the road and your attention off the road. So it's reasonable that that could cause problems. You're putting chemicals into your lungs, so it's reasonable that those chemicals could interact with your lungs. So even though we can't do completely randomized experiments, controlled randomized experiments with some really, really important things, if we can meet all of these criteria, and it's hard to meet all of those, so you can't just throw anything out there and say, oh yeah, that's it. If we can meet all of those criteria, then we can say, yeah, we can come to a conclusion and say, okay, there's some type of strong association. Now, you may still get people that disagree because they might not think that's strong. We talked about how strong can be a relative term and consistent can be a relative term. So there still will be dissent and disagreement, and that's what science is. That's what statistics is how each person interprets that data, and it's about us as the data scientists is being able to really provide arguments or provide evidence about why we came to this conclusion. Nobody's ever going to 100% agree, but we just want to build as much information and as much evidence as we can to say, yeah, even though it is observational, I feel like I can minimize enough confounding by looking at enough of these really, really strict, rigorous criteria. So, all right, so that's it for scope of inference. What do we learn? Who's it apply to? And it comes off of what we were doing randomly. That's it, and I will see you in class tomorrow, guys.